All right, perfect. So now that it is 8 o'clock, we could go ahead and get started. So thank you everyone for joining me for another class in our algebra and number theory session. So kind of to recap, last week we did a good review of like foundational algebra techniques. And this week we're actually going to be building on some of those or some concepts that we learned in an intro class. So if they seem familiar to you, that's really good because what we're going to do is we're going to build on these concepts. If they're unfamiliar, though, we will explain them in enough depth that you should be able to pick them up. But as always, please do ask questions. Okay, but before we get into math, like I said, I like to start off with an icebreaker always. So for today, our icebreaker is if you could have any animal as your pet, what animal would you choose? So go ahead, put your answers in chat, and we'll see. I feel like this one can get really interesting. Oh, okay. Just kidding. Right off the bat, we have two people saying dogs, which are cool. Is there any like specific breed? Okay, I see someone has said a golden retriever. I'll do like a orange. A golden retriever. All right, what else? Hmm. I'll put dog because I think a lot of people say dog. Oh, Amari says a snake. Okay, that's terrifying. I don't like snakes at all, so I think you're really brave for that. Ashu says a frog. Amazing. That's really cool. As long as it's not poisonous, I think frogs are neat. Navya says a sea otter. Very cool, very cool. Kavya says a koala. Oh, I like that. Koalas are nice. Or a Maltese dog. Okay, I've never heard of a Maltese dog. Also, I'm not a dog like aficionado though, so like I probably don't know of any breeds of dogs except for like poodles and golden retrievers. So Maltese, very cool. Avril says I don't like pets, and for the most part, Avril, I'm inclined to agree with you. I'm not a very big animal person. I think there's some cool ones out there. Like my biology teacher had like an albino bearded dragon. So that was like really cool. And she would like bring it to the class and then take it home with her on the weekends. So I think that's like a cool pet. He's like low maintenance too and eats the bugs. So that's really nice. Okay. Rohan says also a golden retriever or a chocolate lab. Okay, I like that. Chocolate lab. Awesome. Rathika says a mini golden doodle. Oh, that's really cute. Okay, a golden doodle. What else? Sean says a snake. Oh, wow, you guys are brave for saying a snake. Rathika says also a red panda. Yeah, I really love red pandas. I would totally have a red panda as a pet. This is like one of my favorite animals, probably. Vihan says a hamster. Yeah, the hamsters are cute. I think hamsters like have a low life what's lifespan. I don't know if that's true. I think they do though. Rashmi says a bunny. Yeah. Actually when I was in first grade, I had a teacher who like would let us take her pet bunny home for the weekends and we could like care for it and stuff. So that was like really nice. It was a nice white bunny. It's very cool. A goldfish. Yeah, goldfish definitely die fast. I know that for sure. But yeah, they don't really do much. They're fish. Cool. Jason also says a hamster. Yeah, awesome. Arjun says a king cobra. Okay, it's still terrifying. Wow. If you guys have ever read Smile, I don't know. Do you guys still read like Smile by like Raina Telgemmer? Or, like, is that still like a thing for you guys? I don't know. But in that book, they definitely talked about like snakes, and that is terrifying to me that her sister wanted a snake. Sean says a Komodo dragon. Yeah, that's really cool. I think I saw one like once in my life. That was trained. Yes, I think that's important. Nahal says a catfish. Yeah, that's really cool. Catfish are neat. Okay. Jason says panda. Yeah, I love pandas. They are so, so adorable. If you guys like watch the World Wildlife Fund feed, camera feed, like they do a lot there. Jason, I see your hand is raised. Let me like get to the end of the chat and then I will come back to you. But yeah, thanks for having something to say. I think that's awesome. It says a hamster as well. Very cool. Manju says a gerbil. Wait, is that similar to a hamster? I feel like it's similar to a hamster, but I don't know. I think it is. Okay, yeah, you guys still read Smile. That's good. That's good. It's like actually it's a pretty decent like comic. I think it's good. Yeah, I'm glad that's still like relevant to you guys. I felt really ancient bringing it up because those books were coming out like when I was like your age. So, yeah, I'm old basically. Wow. Awesome. Okay, yeah, Jason, what were you gonna say? I'm very curious.
I also kind of like uh gerbils. Also,
Yeah.
there's two Arjus that I don't even know who's, you
Oh
know.
yes. Yeah, we actually do have two Arjunes. But yeah, I think sometimes they put their like last initial. So if you guys could do that, that could be helpful in case I happen to call on you. That would be really cool. But yeah, thanks for mentioning that, Jason. Awesome. Okay, yes, Nahal, I have no idea what you put in chat, but that is terrifying. I am quite scared. Yeah. Wow. This is awesome, you guys. Okay, so lots of different animals. This is really cool. I think this is really exciting. Okay, yeah, so I guess this is a good transition point. Let's go ahead and talk about some math now. But first, let's clean up the screen so we have space to do math. So for today, our lesson is going to be about radicals, for the most part. So if you were with us for our intro class, you may be like, oh, radicals are very familiar, which is good. Today, we're going to take it up a notch and kind of look at some more advanced topics because radicals can get very messy very quickly. So I think that is important to understand and be very good with concepts. So let's go ahead and define radicals because maybe you haven't attended our intro class. So you might be like, what is a radical? Which is totally okay. So a radical is basically a root. So we have things called exponents, right? So you guys know like 3 squared. This is 9, right? So the opposite of an exponent is what we call a radical. So we will represent the square root of 9 as 3. So this is our radical. Um, all operations have inverses. So if I have addition, my inverse is subtraction. If I have multiplication, my inverse is division. So the inverse reverses the operation. So if I have like an exponent or a power, the inverse of that is a root or a radical. Because if I take the square root of the 9, then I get back to this original part, which is 3. So this is kind of what we call a radical. So radicals don't always have to be like square roots. This is the most common thing, but you can have like cube roots and fourth roots and all kinds of things. So let's say I had a cube root. Oh, this is like really bad. You'll notice I'm like kind of bad at drawing radical signs. So forgive me for that. It's definitely weirder on like a tablet. Let's see. See if I can like, yeah, okay, this is like, I can work with this. So if I do a cube root of 20, or actually let's just do cube root of 8. What is the cube root of 8? Yeah, it's 2. And the reason why we know this is because 2 cubed is equal to 8. Okay, amazing. So I did see a couple questions in chat. Hitharth asked, does a radical have to equal a square root? Like we said, not necessarily. Radicals are just a general term to describe something with this like sign, this sign. And then, yeah, so like Manji says, essentially a radical is like a root. So you can have square roots, you can have cube roots, you can have fourth roots, I think it's like quartic roots. I don't know. It's really weird. But yeah, you can have all kinds of roots. We will mostly be dealing with radicals, or sorry, square roots. And then there will potentially be some challenge problems with a step up that involve cube roots. So Dorothy asks, isn't this a square root? So what distinguishes this, or what makes this different from a square root is the fact that there's this little 3 here. So if I just have like a symbol like this, and there's nothing in this little space over here, like over here, this is going to be a square root. But if I have this symbol and there's like some number here, like it could be 4, it could be 3, it could even be 7. But if I have a number there, then that's the root we're taking. So this would be a fourth root. This would be a third root or a cube root because of this 3 over here. So yeah, okay, amazing. I think we've clarified this. Okay, Hitharth says, oh yeah, no worries, Hitharth. Take your time. If anything is confusing, you guys definitely ask because I think this is not taught in elementary school at all. Maybe you guys are learning it in 6th grade. I don't think so though. So it's okay if this is like confusing at first. We will go slow. Yes, so Muncha asked, does it have to have a root? Radicals do have to have roots. You cannot have a radical without a root because remember, the radical is what's inversing the exponent. Okay, awesome. Yeah, Rishi, I can definitely go a little slower. We can definitely break this down. Real says we learned this. Okay, cool, cool, cool. Yeah, this is actually 8th grade curriculum, I'm pretty sure. Okay, cool. Awesome. All right, we'll do one more example. I'll introduce to fourth root to you guys. Can you guys find the fourth root of 81? Okay, Monique says three, Avril says three, Mari says three, Rishmi says three. Okay, yes, amazing. And the way you can check this is because we know 3 to the power of 4 is 81. So the thing that inverses it is the radical. So we're kind of going backwards to get 3. Okay, cool. I think you guys kind of understand the premise here. This literally all you have to remember is a radical is that like radicals are backward exponents. Okay, Dorothy says so if it has a number, that's the root. Never heard of that. Yeah, so if there's a number here, that's the root you're gonna be taking. If I just have like the square root of 81, or if I just have like the symbol in 81, there's no like number here, right? So I assume this is a square root. I know this is a square root, so that's why I'll say that it's 9, if that makes sense. So that's like a notation thing. There's not much to prove there. Okay, awesome. Yeah. So for those of you guys who are just joining, we're kind of just talking about radicals and introducing radicals, which encompass square roots, cube roots, fourth roots, all those kinds of things. To recap, essentially a radical is like the backward operation for an exponent. Okay, amazing. So let's talk about some properties for radical. I think I'm going to leave the notation up here just in case like some people need to get acquainted with it. I feel like this font that I'm writing with today is like very skinny. Let's see if I can make this a little bigger. Okay, I'll just like zoom in extraordinarily. Yeah, this should be good. Okay. Yes, I do actually do this for free, but it's because I like to teach. So yeah, that's why I do this. Okay, let's talk about the product properties. So maybe I'll start with an example, see how we go from there. So can you guys tell me, do you think we can simplify? Wait, this is like a bad example. Hold on, because I know we could simplify the square root of 4. Do you think we can simplify this? And if so, what can we simplify it to? Yeah, okay. It seems like a couple of people saying the square root of 15, and I totally agree. Also, thank you guys so much for being very flexible with the chat. I know we can't do like math symbols in there, so this is a little odd for sure. But yeah, root 15, square root of 15, all of those answers are absolutely correct. If you guys want, you can also do like SQRT. That indicates to me that it's a square root. So yeah, if that's less typing, that is good too. Okay, so the product rule is pretty intuitive, very simple to understand. You can basically combine roots that are multiplied together. So this is just equal to the square root of 5 times 3 altogether. And the reason why we can do this in particular is because these have the same base or the same root. So if I had like a square root of 5 multiplied by a cube root of 3, I could not combine this into something with 15, right? Because these are different roots. So it's like kind of like when we have exponents and we have different bases, we can't combine those. We can only combine things with the same base. So this is very, very similar in that sense. Okay, awesome. Oh, hi, Rachel. Thank you so much for joining us. We are talking about radicals today. If you want, you are welcome to review the recording after class to see what you missed. Okay, amazing. So, kind of building on this, now we have the product property. Let's talk about the quotient property. And I'm sure you guys can already guess where I'm going with this. Can we simplify? Um, let's see. What numbers do I want to do? Let's do something bigger. Let's do 21. No, I need to stop doing multiples of 3. Okay. Let's do 35. There we go. I can do 35. Okay. Can we simplify this? Okay, I see from Thorpe that it is square root of 5. Amari says yes, we can simplify. And yeah, that is the gist of it. Yeah, we can simplify this. Because if we can do like multiplication and we can combine like this, we can certainly do division. Because remember, division is just multiplication with fractions. So I can definitely multiply 35 times 1 over 7, and that'll give me 5, or the square root of 5. So pretty simple. Okay, awesome. If it is not simple though, do let me know because this kind of stuff is very important for understanding simple, more complex radical things. But I don't see any questions so far, and everyone has been putting in some answers. Okay, this is great. All right. Yeah, and let's do one more thing. Okay, let's do the square root of 3 to the power of 5. Wow, I am really bad at picking unique numbers. I apologize. Can we rewrite this as something? Okay, this might be like a very silly question. You know what? I don't think this is a question worth asking. I will tell you. You can rewrite this as the square root of 3 to the fifth power. Basically, what this is saying is that you can pull the power of 5 outside from under the root. And actually, this is like really nice because then you can say this as the square root of 3 squared times the square root of 3 squared times the square root of 3, right? Because of our rule where you can like kind of combine the exponents if the bases are the same. So we add all these, we get 2 plus 2 plus 1 is 5. So that matches here, and the base is square root of 3. So when we deconstruct it like this, remember the square root of 3 squared is just 3, right? So this becomes a 3, and then this becomes a 3, and this kind of just remains square root of 3. So this becomes 9 root 3. So like that's like a really neat way to simplify this. I mean, I guess you could expand underneath the radical and be like, oh yeah, the square root of 3 to the power 5 is also the square root of 243, which is also the 9 times the square root of 3. If you don't know that 3 to the power of 5 is 243, like that's kind of a silly method, right? So I think this is much more clever in breaking down the radical and then understanding how you can get the different parts to be whole numbers. Okay, yes. So Arjun and Arav actually put those answers in, so really great work. Okay, Shu asked, question, is the exponent 2 making the radical become the inner number? Yes. So remember, the square root kind of does the opposite of, well, okay, actually, hold on. We can write square roots as like fractional exponents. So if I do 3 to the power of 1/2, this is the square root of 3. So if I do 3 to the power of 1/2, and then I square this becomes 3 to the power of 1/2 times 2, or 3 to the power of 1, or 3. So this is like really important, but also because remember, a radical does the opposite of the exponent. So if I'm taking the square root of something and then I'm squaring it, I'm just getting the exact same number again, right? Because if I perform the inverse operation and I do the normal operation together, the entire point of an inverse is to do the opposite, right? So essentially, I'm just canceling out the operation itself and getting to the original number that I started with. So if I do a square root and then I do a square, those operations cancel out because they're opposites. So then I'm just left with a 3. So those are the two ways that you can understand like why the square root of 3 squared is 3. Okay, just a couple questions. Dorothy says, can you do that again, like another example? Yeah, we'll get to more examples like this kind of towards the bottom. So let me run through the concepts and then we'll come back to that. Okay, MK asks, what is the difference between irrational numbers and radical numbers? Yeah, good question. So, irrational numbers encompass radical numbers, essentially. Basically, an irrational number is something that cannot be expressed as a fraction, but not all irrational numbers are radicals. For example, pi is irrational because you cannot represent pi as a fraction. At the same time, square root of 2 is also irrational because you can't represent square root of 2 as a fraction. Now, there's like a really nice proof for it somewhere. I won't get into it because it's not really relevant to what we're doing. But if you ever go really deep into math, you'll encounter it for sure. But yeah, so irrational numbers are basically like the umbrella around radical numbers. Okay, amazing. Asha says, in that example, because the 2 made the 2. Yeah. So basically, if you want to look at it like the exponents route, that's a good way to see like, okay, if I do 3 to the power of 1/2 and I square it, obviously I get back to 3 to the power of 1. Cool. Okay, Avril says you can represent pi as a fraction, right? No, you actually cannot. So if you guys have seen the pi equals 22/7 thing, that is just an approximation. It's not an actual, like, exact representation. So sometimes you'll use 22/7, but it's not the exact value as pi. So you can't write it as a fraction. Okay, yay. I think I got all the questions, but if I didn't, you can shoot me a message again. Okay, cool. So a couple things about square roots. I think something that can be a little confusing is what the square root value or like the square root function will return. And actually, there's like a really trippy AMC problem. It was like a couple of years ago that really tests your knowledge of like what do square root functions return. So let's kind of cover this idea. Okay, let's do a different number from 3 and 5. I think you guys can tell by now that I don't really like even numbers. I do a lot of my stuff with odd numbers. Okay, let's do 6 squared. What is 6 squared? Yeah, 36. Okay, lovely. I'm so glad we all know our squares. What is negative 6 squared? Yeah, it is also 36. Okay, really good. This is great. So we know that 6 squared is equal to negative 6 squared. This is great. Okay, so I told you guys that the square root is the opposite of the square, or the meaning that if I like take the square root of something, it's going to give me the value that I have to square to get that number. So if I take the square root of 36, most of you guys are saying that's equal to 6, right? But can the square root of 36 also equal -6? Do you guys think that can happen? Okay, Manit says yes. Vihan says yes. Adviti says yes. Nahal says yes. Okay, I'm seeing a lot of yeses. Okay, this is a trick question because the answer is actually no. The square root of 36 is never equal to -6. This is not a true statement. Please remember this. The reason why that is because when we do the square root function, we always assume that it returns the positive value. So yeah, this is like really trippy. There was literally a whole AMC question. It's like number 3 on the AMC 10. I remember because I got it wrong. But it's like number 3 on the AMC 10, and like the question was literally testing your knowledge of like, can square roots be negative? So yeah, I see a lot of people protesting, but we just said that -6 times -6 is 36. Why can the square root of 36 not be -6? The reason why that is because that's how mathematicians define the square root rule. When you're taking a square root, your values are always non-negative. The square root function always returns a non-negative value. You never return a negative value. So that's just the way the function is defined. And that's why the square root of 36 is never equal to -6. So if you ever see a problem that's like taking the square root of something, always assume that you're talking about the positive root and not the negative root. That's really important. Okay, awesome. Yay. Glad we are all on the same page. Okay, let's see. What else can we talk about? Yeah, okay, I think all of this is pretty simple. Yay, I'm so glad we all get it. Okay, let's now talk about adding and subtracting. So we did multiplication and division. Adding and subtracting seem like weird. Well, it can get weird. It can get weird if you're not careful. So let's clean this up. Cool. I don't know what I did. Why does it look like that? Okay. All right. So the golden rule when you're adding and subtracting radicals is you can only do it if they have the same thing underneath the radical. So, okay, hold on. Let's do some definitions really quick, because this might be a little easier. Let's do like a dark green. Okay, so let's say I have like the square, or yeah, let's say I have the cube root of 13. Okay, so the thing underneath the radical, we call this a radicand. Radicand. And this thing we call the root. So I will be using these words quite a bit, so just make sure you're familiar with them so you're not like, oh my gosh, what does she mean when she says the radicand? I'll like leave this over here though, so if you ever need to look at it, you can. Okay, so basically we can only add or subtract radicals if they have the same radicand, this thing over here. This is kind of like the rule in exponents where we can only like multiply or divide radicals if they have the same base. So like we can only do like 2 squared times 2 cubed is equal to 2 to the power 5. We can't combine like 2 squared times 3 squared into something, or 2 squared times 3 cubed. Like that doesn't work. So yeah, that it's like the same idea. So hopefully that will help you guys like understand why this is so. Radicant. Yeah, it's radicand with a T. Okay, amazing. What color should I use? Wait, I said last class I would let you guys pick the colors. So what color should I use for now? Oh, red from Amari. Okay, great. I don't think I have a pink. Maybe I can add a pink though. Okay, I'll do red and then I'll do blue after this. Let's do this bright red. Great. Let's see. Okay, so let's start off with this first very easy example just to make sure we understand like when we can combine things, and then we'll take it up a notch. So what does this come out to be? What is the numerical value? 4 root 3 plus 2 root 3. Okay, awesome. I think the first answer I saw was from Kavya, and it is 6 root 3, which is absolutely correct. Like I said, the reason why we can combine these is because the radicand 3 is the same in both. So that means we can go ahead and combine these coefficients. So 4 plus 2 is equal to 6, and then we throw on the root 3 at the end. So if I have this like coefficient hanging out front, that means this is 4 times the square root of 3. So that's why we're able to add these 4 and 2's and then multiply by 3 at the end. It's kind of like a distributive property almost, like reverse distributive property. Okay, now let's say I had, okay, this is like simple, so I'm gonna like take it up like 10 steps and see how you guys do. Let's say I did 3 cube root 5 plus 2 cube root 5 minus 5 root 2 minus 3 root 2 plus root 3. What is this equal to? Oh, wow. It looks like some people are starting to get the square root stuff. This is interesting. Arjun, if you want to put in like the code for how you did that, that would be really awesome. Yeah, I'll give you a couple seconds for this one. My tip to you guys is to stay organized, because this is definitely something where if you don't stay organized and keep track of your numbers, it's gonna get a little messy. Okay, awesome. I see an answer from Aral, who has painstakingly wrote out all the things. So thank you so much, Aral. Okay, I think the first answer I'm seeing is 5 cube root 5. Wow. I need to get better at writing these radicals, you guys. I so apologize. And then I see like a -8 root 2. Is that correct? Okay, yeah, and then plus root 3. Okay, so I see a couple of answers, but I also see some people are like, what is happening? Which is totally cool. This is like definitely like much more difficult than this question. So it's okay if you guys are a little lost, like what is going on? Oh, it seems like Nahal has also got a square root thing. I think if you do, I don't know, I'll mess with this in a second. Okay, so let's first talk about this question, right? The golden rule, you can only combine things that have the same radicand and also the same root actually. So this root has to be the same and the radicand has to be the same. So if I see right here, I can combine the cube root of 5 and the cube root of 5. Because the root is the same, they're both cube roots, and the thing underneath the radical, the radicand, is also the same. So this 5 and 5 are same. So I can combine these together to get 5 cube root 5. Okay, now I look at my next term, which is 5 root 2 and 3 root 2. Because now I'm looking at square roots and I see under both radicals the 2 is the same, I can go ahead and combine these. So then I get -5 and -3 combined is -8. And then I just slap on that root 2 at the end. So -8 root 2. Okay? And then finally I'm left with this like lonely root 3 that's kind of just hanging out here. So then I put this root 3 at the end. And this is the simplified expression for this really long thing over here. So for those of you guys that were a little confused before, does that explanation like make a little more sense? Do you understand how this is happening? Oh wow, so many people have figured out these square root things. Amazing. Okay, yes, everyone is on the same page. Okay, awesome. So adding and subtracting radicals isn't super difficult as long as you understand that everything underneath the radicand has to be the same as the root. Okay, awesome. Let's do one more problem just to double check, and then we will move on. Let's see. This one is like similar, but it's got a little twist. So can you guys simplify 3 root 8 plus 2 root 2? Okay, I see color who's saying 8 root 2. Interesting, interesting. Do you guys have a numlock? I don't know. Oh, okay. Cool. All right, so I see most people saying 8 root 2. All right, let's take a look at why this is. So some of you guys might be like, how can we combine these if the radicand is not the same? And technically you are correct, but we can actually simplify the square root of 8. So if you look at square root of 8, this is actually equal to the square root of 4 times the square root of 2. What is the square root of 4? Yeah, it's just 2. Perfect, because 2 squared is 4, so the square root of 4 is just 2. Very good. So that means that this is going to be 3 times 2 times the square root of 2 plus 2 times the square root of 2. So this comes out to be 6 times the square root of 2 plus 2 times the square root of 2. And because the radicands are now the same, we can go ahead and add these coefficients over here. So that becomes 8 root 2, which is our final answer. Okay, awesome. So the big idea here is if at first you can't seem to simplify anything, see if you can simplify one of the radicals and then kind of work from there. I think that will definitely help in terms of simplification. Okay, amazing. Yeah, this is like basically what you have to know for adding and subtracting radicals. Um, yeah, and if you guys want extra practice, there will definitely be some in the homework. So we can definitely go, oh yeah, okay, wait, just kidding. I see a lot of people asking for more examples. So we'll do one last one, and then after that, we'll include extra problems in the practice. Okay, let's see. Which one should I do? Which one will be helpful to you guys? Uh, okay. Let's do. Mhm. I'm trying to think like what could like what's gonna be the most beneficial. So I think we should do this one. Um, 5 root 12 minus root 3. Can you guys simplify this for me? Okay, I see a couple people saying 9 root 3. So let's go ahead and take a look where this comes from. So right now, I don't think I can simplify this. I can't combine anything because the square root of 12 and the square root of 3 are not the same. So I can't combine here. What I can do, however, is break down the square root of 12 into its factors. So this will become the square root of 4 and the square root of 3. So if I go ahead and simplify this, the square root of 4 is 2. So essentially 5 root 12 is equal to 5 times the square root of 4 times the square root of 3. And I know the square root of 4 is just 2. So this becomes 5 times 2 times the square root of 3. So this becomes 10 times the square root of 3. So if I go back to this equation over here, that means I have 10 times the square root of 3 minus the square root of 3. So because these are the same, you can kind of think of it as like literally backwards distributive property. That is the best way I can say it. So instead of like square root of 3, if that's confusing you guys, just think of it as like a variable, like an x or like a heart or something. So this is like 10x minus x, right? And that's just 9x. We said that x is the square root of 3, so we can go ahead and put that square root of 3 back in. So this is 9 times the square root of 3. So that part that's confusing you is like, how do we collapse the coefficients? This is why we can do it. It's because essentially all you're doing is just multiplying the radical by some whole number and then combining from there. Okay, hopefully that makes a little more sense. If not, we can talk after class. Okay, amazing. Let's go ahead and transition. Yes, I can speak slower. I'm sorry. Sometimes I talk really fast. That's just me. But I will slow it down a little. Okay. Um, Wait, this is awkward. How do I minimize this? No, leave it. Unfortunately, I can't leave it because I need to create some space to write. But you can see all of this in the recordings. Yeah, okay. Cool. So now we're really getting to the meat and potatoes of today's class, which is multiplying radicals. And if you took our intro class, you might be like, okay, everything Sam just did, I'm pretty good with. Maybe the problems are different. Maybe they're a little harder. So today is like, now we're gonna hit the part where we really bring in some new stuff. So multiplying radicals. This can get really tricky, which is why it's important to make sure you're following along with me here and asking questions where needed. So the big idea when you're multiplying radicals is FOIL. How many of you guys have heard of FOIL before? Okay, lots of people have heard of FOIL, which is really great. So typically when you use FOIL, you do it with like maybe two-digit numbers, or maybe you do it with two-digit properties. Um, yeah. So this is kind of what FOIL is used for. Now, if you're wondering, like Amari, am I talking about aluminum foil? No, I am not actually. So FOIL is a cool acronym we use in the math world that stands for first, inner, outer, last. I guess that spells feel. Hold on. Let's switch this so it actually spells foil. Oh, it seems like everyone thought I was talking about like actual aluminum foil. Okay. Well, I'm talking about the math method foil. Maybe I should have clarified that. Inner. Okay. Maybe this still doesn't mean anything to you because you're like, okay, she's just writing some adjectives on here. This is not cool. So let's do kind of an example with just some numbers first, and then we'll take it up a notch. Okay, so let's say I want to multiply like 23 and 17. Okay. I guess you could do this like this, which is like great and all, but you can also do it like horizontally. So the way we're gonna do it horizontally is we're gonna break this up into its parts. So we'll do 20 plus 3 times 10 plus 17. And now you apply distributive property, which I know you guys all know because that doesn't stand for any acronym, and you guys have definitely learned distributive property before. So what we're going to do is we're going to do the first. Okay, that's the first step we're going to take. So I'm going to do this in red. That's going to be the first terms multiplied together, which is 20 times 20. Okay, then I'm going to do the outer terms. So that's going to be the terms on the outsides of the parentheses. So that's going to be 20 times 7. Okay, and then I'm going to do the inner terms. So this is going to be the terms inside the parentheses closest to each other. So that's going to be 3 and 10. And finally, I'm going to do the last terms. So these are going to be the last terms in the parentheses. So 3 times 7. And if you'll notice, after I've gone through this entire process, I've covered every single possibility for multiplying the terms together. So if I multiply all of this out and simplify, I will get, let's do this in black. Normally I don't like to use black, but it's okay. I will get 200 plus 140 plus 30 plus 21. And if I add this up, I will get 200 plus 170 plus 21, which is 391. And I saw a lot of people put this in chat, so that is absolutely correct. So FOIL is kind of a good way to use it's basically like a way to use distributive property, essentially. And it's really important when you're doing like maybe 2-digit multiplications or 3-digit multiplications. Okay, so that was like a brief intro to FOIL. If you are not familiar with this, I do think we talk about this in our like old number sense class. So yeah. Yeah. Okay, cool, cool, cool. Let's now transition to radicals. So we can also do FOIL with radicals. There we go. That's what I was looking for. Okay, so in the same way, all we're doing is instead of having like whole numbers like this, we're just gonna have some like square roots and some radical signs. But we're gonna do the exact same multiplication and simplifications. Okay, cool. Seems like some people are saying, how are you able to draw so fast? I have a tablet. Yes. If you stay after class, I will show you my tablet. Okay. Cool. And then after we do our like multiplication and stuff, that's when we combine all the terms. So that's why I taught you guys how to add and subtract radicals before I did this, because if you don't know how to add and subtract radicals, you won't be able to finish the final step of the FOIL process. Okay, awesome. Yeah, thanks for letting me know, Amari. Go ahead. Okay, so let's go ahead and just start with a simple example with just numbers. So we're going to do the most barest thing ever, so that way we can understand how this works. Let's see. I thought people wanted blue. I haven't done blue yet. I'm so sorry, you guys. I think we did light blue, so I will do a dark blue now. All right, so here's our question. Can you guys expand the square root of 2 plus the square root of 3? Oh, I see a lot of people saying coral. Yes, I will pull that up next. That's a custom color, but I will see if I can do that. Okay, times the square root of 3 plus the square root of 5. So take a couple of seconds, see if you can apply the FOIL method here. And if you're kind of confused with the radicals, just think about what we did with 23 times 17. Actually, this is one step less because we don't have to break 23 and 17 into 20 plus 3 and 10 plus 7. Instead, we go straight into doing our FOIL method. So we just multiply based on FOIL. So go ahead, take a couple seconds, and then we'll talk. Yeah, so Tanish asked for a brief recap of radicals. So essentially, radicals are just like backwards exponents. So in exponents, I'm like doing something like 2 cubed, and I get to 8. But in radicals, I will take the cube root of 8 to get to 2. So I get back to the base power of whatever I raised my thing to, whatever exponent I raised my base to. So radicals are essentially backwards exponents. And what else is really important to know? Radicals can be square roots, cube roots, fourth roots, all kinds of things. But yeah, radicals essentially look like this. Not all radicals can be simplified. Tanish asked, do we combine like terms? Yes, go ahead and fully simplify this so that you have as few terms as possible. Okay, I see a couple people saying square root of 40. All right, we will see. I also see some people with longer answers like 6 plus root 7 plus root 8. Okay, awesome. Yeah. Okay, let's take a look. So, starting off with FOIL, right? So I'm going to start off with the first terms. I said I would do that in red, right? Okay, so the first term is multiplied. is square root of 2 times the square root of 3. So square root of 2 times square root of 3. Okay, next I'm going to multiply outer terms. So my outer term is the square root of 2 and the square root of 5, because those are the things at the very, very ends of this entire expression. So square root of 2 times square root of 5. Okay, so I'm going to add that. Awesome. Now, wait, I think I need a little more space. Let's scoot this over here. Okay. What did I say I would do inner and orange? Okay, now I'm going to do the inner terms. So that's going to be the stuff closest together in the middle of the parentheses, which is square root of 3 times square root of 3. And then finally, I'm going to do my last terms multiplied together. So the last terms in each parenthesis, that's going to be square root of 3 times square root of 5. All right, so I'm going to pause here and see, does everyone see why this expression over here is equal to this expression over here? Is that clear to everyone? Because this is a really important step. Okay, it is clear. Awesome. Okay, so now is the easy part. Now is the simplification part. Let's see. I'll do like dark purple for this. Okay, so square root of 2 times square root of 3, we can just use the product rule here. So this will be the square root of 2 times 3, or the square root of 6. Then the square root of 2 times the square root of 5 is just going to be the square root of 2 times 5, which is the square root of 10. Then the square root of 3 times the square root of 3 is actually just going to be 3, because these are the exact same. So this is the square root of 3 squared. So this is just going to be equal to 3, which I think is very nice. And then finally, you're going to have the square root of 3 times the square root of 5, which is the square root of 3 times 5. That's the square root of 15. And this is actually our final answer. You can't simplify this anymore, because none of these square roots can be broken down into anything else. Like, this is the most simplified square root. Some people will say, oh, you should write your 3 at the beginning because it's an integer. You can do that if you want. I think that's like kind of dumb now that we have our final answer. So yeah, this is essentially all you have to do. Great. So I know a lot of people were saying square root of 40, and I think the reason why that is because you guys did the square root of 2 plus 3. So the square root of 5 times the square root of 8 over here. But remember, we can't combine square roots if the radicand, the thing underneath the radical, is different. So the square root of 2 plus the square root of 3 is not equal to the square root of 5. That's really important. So if you ever see this kind of expression, do not do not combine these together to get one square root. You have to use FOIL. There's literally no easier way to do this. Otherwise, I would tell you guys, you have to use FOIL. So if you don't like FOIL, I am sorry. I hope you come to enjoy it after doing many problems, because it is everywhere. And yeah, hopefully you will enjoy it at some point. Okay, so that's how we do this with just some numbers. With some coefficients, it's like pretty similar. So I kind of want to do like a couple of questions, and then we will maybe see if we have time for like rationalizing denominators of fractions. Okay, Ashia asked the question, how did you get 3 from square root of 3 times the square root of 3? Okay, good question. Remember, 3 squared is equal to, or sorry, the square root of 3 squared is equal to 3. Hold on. This is like, never mind. That was really a bad explanation, because that was just very circular reasoning. We can write the square root of 3 as 3 to the power of 1/2, right? So if I do 3 to the power of 1/2 times 3 to the power of 1/2, this is equal to 3 to the power of 1, because I add the exponents. So that's just 3. So this shows like why the square root of 3 times the square root of 3 is 3. Also, remember, a square root just means you're taking like you're kind of taking like the half of the exponent. Okay, cool. Cool. All right, I think we're all good, all on the same page. So let's do a couple of challenge problems, and I really hope we have time for rationalizing denominators, at least like the initial portion of it, because I actually meant to cover those like last week. Apparently I teach really slow, but it's okay, as long as everyone is understanding. That is what is most important to me. So if I need to go slow, that's good. Okay, cool. All right, let's do some challenging problems. These are going to add some extra complexity. Maybe you'll see some coefficients, maybe you'll see some variables even, but do not fret. All you have to remember is FOIL. First, outer, inner, last. Eat, sleep, breathe, foil. Okay, you guys, this is like super important. All right, let's get on to it. I think I don't want to write this out anymore, so I'm gonna start taking screenshots. Let's start off simple because I don't want to like scare you guys. We'll start off with this question. Yes, and I will, while you guys are solving, I will find the coral. I will get coral. Okay, awesome. So go ahead, take a shot at this question, and then we will see if I can find some coral. Coral's like pinkish, reddish, orangish, maybe. Hmm. Oh wait, I feel like is this like coral? I feel like this is coral. Wait, I feel like coral's more orange though. Hmm. Tiny bit lighter and oranger. Wait, I actually have no idea how to make this orange. Like maybe I need to go on the other side. Oh yes. Okay, hold on. This is like good. Okay. Uh, Lighter, right? Wait, this looks more peachy. Sorry, this is like definitely not math related at all. It is next to red. Okay. Wait, I think this is coral. This is like the best. Oh, are you guys talking about this? This is red. This is not coral. Okay, I will use this color. The one next to it. Oh, this one? Is this coral? Oh, okay, cool. Okay, this is cool. All right, sorry guys. Okay, now after that brief intermission, it seems like we have answers. Thank you guys for putting up with me. Cool. It seems like some people are saying 14 and 5. All right, let's take a look. Oh, actually, okay, wait, this is such a unique question because technically you don't even have to use FOIL. I'm going to show you the FOIL method, and then I'm going to show you the other method. So starting off with FOIL, I'm going to do first square root of 7 times square root of 7 plus outer square root of 7 minus the square root of 2 plus inner, hold on, this is like, there we go, square root of 2, plus the inner terms, which is square root of 2 times square root of 7, and then plus the last terms. So the square root of 2 times this negative square root of 2. It's negative square root of 2. Okay. Let me make this a little thicker just so you guys can see it. Okay. So going ahead and simplifying, yeah, I'll finish off with coral just for this question because I know a lot of people were asking for it, and then we'll go to a darker color. Yeah. Okay, so square root of 7 times square root of 7 is going to be 7, right? Because if you square a square root, you just get the number underneath the radicand. Okay, and actually something really neat is that these two terms will cancel out because of the negative. So these two will go away, and then I'm just left with the square root of 2 times the negative square root of 2, which is just negative 2. So my entire thing is 7 minus 2, which is 5. Isn't that so weird that we're getting a whole number after multiplying radicals? Like, isn't that so whack? Um, yeah, this is pretty whack. But the reason why that is because of a special property we call difference of two squares. This is actually something we learned in one of our previous classes. So if you attended that, maybe this is like, okay, wow, I didn't even have to do FOIL. Like this is pretty neat. So what we can see here is the square root of 7. The difference of two squares thing is kind of like you have, um, let's see, how should I explain this? Basically, you have something of the form like a plus b times a minus b, right? And when you do some expansion, this essentially comes out to be a squared minus b squared. I would show you the expansion, but I want to save time to get onto some more interesting stuff. So because of that, all you have to do here is the square root of 7 squared minus the square root of 2 squared, which is 7 minus 2 equals 5. And that is our final answer. Okay, amazing. All right, we'll do one more question and then we'll start talking about rationalizing. Yeah, okay, some people have like, oh, we've done this before, which is good. Okay, if we can cool up on the colors, that would be great. I will do teal now. But yeah, let's keep the color recommendations to the minimum. Okay, people are saying darkest color. Okay, before I do that though, let's talk about our question, which is gonna be this thing. Okay, awesome. Let's go ahead and approach this. I'll give you guys a couple seconds and then we'll talk. wait, I don't want this. I feel like this is a good deal. Okay. All right, awesome. I do see your first answer, but I will wait for everyone to be able to put some stuff in just to see what we're looking like. Okay, I see a couple people saying 19 plus 7 square root of 15. Awesome. All right, let's take a look and see where this kind of comes from. Yeah, this is difficult, right? So I've definitely added a layer of complexity here because now we've got these coefficients out front, right? So wait, that's not a coefficient. This is the coefficient. But at the end of the day, all you have to remember is FOIL. This is like the golden rule, okay? So what we're gonna do is first terms, right? So we're gonna do this term and this term over here. So 3 root 3 times root 3, okay? Those are our first two terms multiplied together. Then I'm gonna do my outer terms. So the terms on the outside of the parentheses. That's gonna be 3 root 3 times 2 root 5. 2 root 5. Okay, and then I'm going to do my inner terms. So the terms on the inside of the parentheses closest to the middle. So that's going to be square root of 5 times square root of 3. And finally, I'm going to do my last terms. So the terms at the ends of both parentheses. So that's going to be square root of 5 times 2 square root of 5. Okay, awesome. So let's now see how we can simplify this. All you have to do is be very, very careful with simplifying and then combining like terms. So starting off with the beginning, we have 3 times the square root of 3 times the square root of 3. That's going to be 3 times 3 because square root of 3 times square root of 3 is 3. Okay, then we're going to add this with 3 times 2 times square root of 3 times square root of 5. So the 3 and the 2 will combine to become a 6. And then the square root of 3 and the square root of 5 will combine to become 15. Okay? Then we have square root of 5 times square root of 3. So this will also be square root of 15. And then at the end, we will have 2 square root of 5 times square root of 5. So we'll get the 2 at the beginning, and then square root of 5 times square root of 5 is equal to 5. All right, how do we all feel about that simplification? Does that make sense what we did here? Yes and no. Wow. Okay. So it seems like we're pretty split here. Let me recap one more time, just really briefly. So breaking it down, we'll start off with this first term, okay? Remember with radicals, with coefficients, even though it seems like they're kind of just stuck together, you have to remember that 3 times the square root of 3, for example, is 3 times the square root of 3. So there's a multiplication involved here. So if I have 3 root 3 times root 3, this is 3 times the square root of 3 times the square root of 3, right? So we can use a little bit of associative property here, right? We can say that I can simplify this term together. So this becomes 3 times 3. We know that the square root of 3 times the square root of 3 is 3. So this is where the simplification is coming from. That's the big step here. Does that make sense, you guys? Yeah? Okay, awesome sauce. Cool. So we kind of go on a similar process like that. I think the hardest one here to simplify is this stuff, because there's like 50 different things going on. So let's actually break that down. And the rest I think is like pretty self-explanatory. So we'll do 3 root 3 times 2 root 5. Okay, so this is 3 times the square root of 3 times 2 times the square root of 5. So I can like rearrange these terms, right, by the commutative property. So I will say this is 3 times 2 times the square root of 3 times the square root of 5. So I know that 3 times 2 is 6. So I'm going to say this is 6. But I also know that the square root of 3 times the square root of 5 is also equal to the square root of 3 times 5. But that comes out to be 6 times the square root of 15. But this comes out to be 6 square root of 15. These are just equal. All I'm doing is taking away this one step in the middle. Oh yes, let me pause here and like just let you guys absorb this. Yes, let me do that. But I hope this makes like a little more sense about where this simplification is coming from, because that is very important. Okay, great. I think some people are getting it now, which is awesome. Yeah, and if this is like still like not clicking, please go back and watch the recordings. And if it still doesn't make sense, shoot me an email. But I think the more you guys practice with these kinds of problems, the easier it gets. I think like because right now, it's definitely like you're under a time crunch for sure. And then also it's just like this is the first time you're seeing a lot of this sometimes. So yeah. Okay, MK asks, wait, so you have to multiply in addition and subtraction. Um, I'm not sure I understand what you mean. Yeah. Could you clarify your question? That'd be helpful. Okay. Uh, when will we get into quadratics? Quadratics will be like, I hope we can do quadratics in like maybe like mid-September is my goal. But yes, that's like gonna be like towards the end of our algebra section. But we'll spend like definitely quite a few weeks on quadratics. There's a lot to explore there. So that's like 2 or 3 weeks for quadratics for sure. But yeah, awesome, awesome. Okay, cool. All right. I think everyone is like on the same page. If we have questions though, please ask. Okay, great. I think we're good. Okay, I did want to get to rationalizing, but that's okay. Maybe we'll save this for another class. Maybe this will be like a bonus topic. We will see. All right, we'll do one more question just because we have some extra time. Oh, I do have one question though before I move on. Do you like multiply the radicands and coefficients in addition and subtractions? No. So if I'm adding and subtracting radicals, like I think you're talking about like if I have like 4 root 3 plus 2 root 3, I don't do anything with the radicands. All I'm doing is adding the coefficients. So I will do 4 plus 2 times square root of 3. So this is 6 times the square root of 3. Does that make sense? Okay, cool. All right, so let's return back to our question. Yeah, now we're here, right? Yes, there is no addition and subtraction when you're just like when you or yeah, not here. Yeah. Okay, cool. Okay, so let's click this up. Oh no, where did it go? Okay, cool. So now we've got this step. We're not done yet. We still have to finish simplifying. I know 3 times 3 is 9, and I know 2 times 5 is 10. So I have 9 plus 10 is 19. Okay, and then I have 6 times the square root of 15 plus the square root of 15, and that comes out to be 7 times the square root of 15. So this is my final answer. Does that sound right? I know a lot of you guys put 19 plus 6 square root of 15. So if you guys think I did something wrong, let me know because that can happen sometimes. Sometimes I just do wrong math. So yeah, take a second, see if you guys understand like how this problem happened. Awesome. Okay, cool, cool, cool. Okay, I think we're good here. How did I get 7? Oh, yes. Okay, so I did 6 times the square root of 15 plus, there's like an implicit 1 here. So we don't write it, but it exists, right? So the coefficient for the square root of 15 is 1. So then when I add these together, I get 6 plus 1 times the square root of 15, which is 7 times the square root of 15. Okay. Awesome. So hopefully that explains where that comes from. Okay, yeah, so it seems like some people forgot the inner thing, which is totally okay. Remember, if you forget inner, that just spells out full, which is kind of silly. You should always be spelling out FOIL with your math. Okay. Is there any chance you might talk about ratios and box plots because I saw them in the diagnostic and have no idea what they are? Yes, we will get to ratios and box plots for sure. That will probably be like towards the middle of our class, maybe in a couple weeks. Yeah, cool. Yes, I can slow down. Actually, there is nothing, there is no more for me to slow down. But I will try to be slower in the first class, in the next classes. So yeah, I do talk really fast. So please tell me to slow down as needed, whenever. Okay, and it is actually 9 o'clock now. So let's go ahead and conclude class. If you guys have questions or like just a burning concern, you have to tell me, like, please stay and we will talk. But yeah. Okay, let's see. Where am I from? I am from Lambert High School in Forsyth County, Georgia. Yes. Cool. In diagnostics, I got pre-calc and I started guessing. Oh yeah, there's definitely some crazy stuff in the diagnostics. So it's okay if you guessed. That's totally okay. It's a diagnostic for a reason. Yes, we will definitely talk about functions. Functions are really important in algebra, so that's something that we'll address I think hopefully like before quadratics, but like it might go after, depending on what we do with functions. Yeah, okay. We will do a little bit of statistics, because I think statistics is really cool. If not in this class, we will do like a separate like webinar type thing with statistics. Okay, awesome. Can we play a game to review? Oh, that's a good idea. Maybe we can do like a game review after like a couple of weeks of like all the content we've done. I like this. This is good. That's a good idea. Okay, awesome. Yeah, interquartile range. Yes, we will definitely be talking. Hopefully we get to talk about this stuff and like box and whisker plots. That'd be really cool. Probability, I kind of want to save that for our counting and probability class, so I don't think we'll really be doing that in this class. Yeah. Oh, it's cool that you guys like probability. AS asks if we're going to do functions on a graph. Hopefully that is the goal. Yeah, if we do quadratics, there will definitely be graphing involved. So I hope we can also do some functions and graphing. Yeah. Oh, some of you guys got trig. Man, that sucks. Trig sucks. I don't like trig. Cypherny says, I started to get finding the circumference of circles. Yeah, well, if you didn't know how to find the circumference, we are running a geometry class where we will eventually talk about that. Okay, yeah. Yeah, bye everyone. Thank you so much. Thank you so much for joining. Awesome. Yeah, thank you guys so much for attending. I really appreciate it. This is fun for me. Okay, yeah, so I know some people would like to go over things. So if you guys are still here for that, feel free to unmute and we can talk. I think Dorothy, I'll let you unmute for now.
Mm.
Hi. Bye, Amari. The subject for next week has not been decided yet. I actually don't know now. Okay, awesome. All right, Dorothy, what did you want to go over?
I just want to do like one more problem on the foil because like I kind of didn't get it.
Yeah, no, that's totally okay. All right, we can do one more FOIL question. Let's start, like, I think it's really important to understand like the basic FOILs, and then after that, like, it becomes really clear how you can add like coefficients and variables and stuff. So we'll do like one FOIL with just like some simple numbers. Um,
Because I tried doing binomials once.
yeah,
I kind of got it, but then like it's been a couple months, so I kind of forgot. But
yeah.
I